For this distribution, think about a process with only two possible outcomes. For instance, whether it's a rainy day or not, or when flipping a coin, whether you get heads or tails. Then imagine a series of these processes. In the example of flipping a coin, let's say that you do the experiment of flipping the coin 10 times. Now, because each time you have a 50% chance on getting heads, on average, after 10 flips, you will get 5 times heads. But of course, you could also get 6 times heads and 4 times tails, or 7 times heads and 3 times tails, all the way to 10 times heads and 0 times tails. But this will of course be very unlikely. Now, if you do this experiment of flipping this coin 10 times over and over again, and after each experiment collect the number of heads that you got after 10 times, then this entire data set as a whole will be distributed according to the binomial distribution. Now, describing this process, the binomial distribution requires two parameters. The first one is the number of trials. In the case of our coin flipping experiment, this would be 10, because each experiment existed of 10 trials. The second parameter is the probability of success. In the case of a fair coin, that would be 50%. But of course, if the coin is biased to get 70% of the times heads, then this will be 0.7 or 70%. Now again, looking at our figures, we see that the binomial distribution is a discrete distribution. And this makes sense if we think about our coin flipping experiment. If you do this experiment of flipping a coin 10 times over and over again, and your random variable is the number of heads you get after flipping the coin 10 times, then this could be either 0, 1, 2, 3, 4, 5, all the way up to 10. Again, discrete variables. And in this specific case, we see again that our histogram is sometimes above the theoretical value, which are these dots, and sometimes it is below it. And the same for the cumulative distribution function. So how do we generate such data sets in Python code? Well, again, very simple. We first define n, which will be the number of trials, and then we define p to be the probability of success. Now, the values that I chose in this case is that we have 10 number of trials with a probability of success to be 50%, or the exact case that I described with flipping a coin 10 times. Now let's see how we would change these numbers if we are looking at the example of the rainy days per month. So let's say that the probability of having a rainy day on each given day is equal to, let's say, 20%. And the number of trials, so the number of times that we will look at a specific day and see whether it is rainy or not, is 30, because we want to know the amount of rainy days in this scenario on any given month. So if we run this example, then what we would get is a distribution looking at the number of rainy days that we would get in 1 month. So if we scroll down and we look at not the Poisson distribution, but the binomial distribution, then we can see here on the x-axis the expected value that we would get for the number of rainy days in 1 month. So let's see, the most common value, the theoretical value, which are the dots, is 6 days. So if there is a 1 in 5 chance, 20%, of being a rainy day on any given day, then in 1 month you would expect to have on average 6 rainy days. But of course, you could also have, as you can see, 14 rainy days, which is very unfortunate, of course. So let's now go back to the slides and learn about the final distribution function, which will again be a continuous one, namely the Rayleigh distribution.